fast in terms of inference in both directions. We tried Markov logic networks first, due to some prior work, but they have a really tough parameter tuning problem and don't do well in the reverse direction. But what it enables us to do is to ask different kinds of queries. Let's just say, where I want a spoon, where can I find it, right? And it gives you a probability distribution over all locations. And I can also say, I'm looking at the kitchen counter, and I'm seeing an object I don't know. Give me a probability distribution over all things that could be located on kitchen counters, because that can help me maybe decide what this thing is, right? So these are two examples of the kind of inference you can run, and it looks something like this. And one way to test it is we went to computer vision because why not? We have these nice general images you can pull in from computer vision where they've labeled all the objects. And we can look at how accurate our model is at running inference, at guessing appropriate object locations or their uses and so on. And it turns out that we do really well. Everything's in like this range, so 75% is the lowest we do. Mostly the average is like 87 or something like that, which is pretty good given that all we're doing is just looking at a scene. It's cool that we can already tell you the utensils are in drawers. And what's interesting is the more words we have, the more we know about a scene, the better this works. And the reason is that the more information we have about what else in the scene, the more it helps us to figure out that this cup is the actual drinking cup, not the soccer World Cup type of cup. Which, you know, that is not the problem. We have still a problem with a sink. We have not solved that one. It still thinks the definition it should use is cesspool. Like, no, this is not the right definition. So you never knew how many definitions words have until you work on something like this. And what we're working now, so all of that, by the way, is really abstract information. So the graph I just had is the one up here. But now we're putting it on a robot and wanting to have the robot go up and enter a room that we have a kitchen now built in our lab, and you want the robot, now I want to be able to say, where are the spoons? And I should be like, I would try those drawers, right? And it should know, and if it can't find it in the drawers, where else should it look, right? There should be some sense in the way the robot behaves. That requires solving this complicated problem of grounding and instances and the fact that sock drawers are drawers and utensil drawers are drawers, but you don't usually put socks and utensils in the same drawer, and we're working on that right now. So this is, any comments or questions on that? This is kind of really early stage right now in terms of this we kind of figured out, but now the project is moving on to kind of looking at more situated interaction with an actual robot. Okay? All right, so then let me very, very quickly talk about learning. I'm going to skip a bunch of it. I'll tell you about our crowdsourcing project very briefly. This was done a while ago. We had a new robot, which was this PR2 at the time. And we wanted it to be able to manipulate or recognize and pick up as many objects as you can. It's something you guys take for granted maybe, but it's really sometimes hard for robots. It's getting easier. We wanted to find a way to get the robot to very efficiently and quickly learn about robot models. Back then, a lot of people were still using turntables, like putting an object on a turntable and spinning it while a laser's looking at it and building a careful 3D model. And we didn't want to mess with that kind of stuff. Plus, we had other goals in mind. We really wanted to tackle the usability aspect that I talked about at the beginning. We wanted to get our robot access, or other people access to our robot. Long story short, what we developed is a web-based framework for robotics. And this is something that we started in 2012. We still have it running here. It's a huge part of our lab, and roughly 2 other places in the world really have something like this, where our robots, or not all of them, but several are accessible to be controlled in real time over the web. So we have really nice web interfaces that enable people to do whatever we want them to do. We can kind of open it up, different levels of control, and we can have people we don't know somewhere across the world. We've literally done user studies with people all the way across the world in Asia, where they're interacting and teaching our robots. And that's really freeing from, we still recruit users from campus as well, but this is really an interesting way to do research. It really opens it up. And just to give you an idea of what that looks like, this is our first project with it, where what you're seeing on top is the way a robot looks to us in the lab. It's just standing at a table and it's moving. This is what users see. It's a browser, like Chrome or whatever. I think we mainly stick to Chrome and Firefox. And in this case, they have two screens. On the left, they have this big arrows called interactive markers. And when they drag on the arrows or rotate these rings, the wrist moves. Now, there's 6 degrees of freedom for the wrist, and so you can control that. And what they're doing here is they're playing a game. This is kind of a gamified task where we're trying to learn these 3D models of objects and where to place the gripper. But to users, it looks like a game where they're trying to pick up as many objects as they can in 15 minutes. And in fact, giving them points makes them pick up twice as many objects as they otherwise would. And the research behind it is that I'm going to kind of skip over it each time, but we can build these 3D models with no prior information about the orientation of the object, what it is, what size is it, anything else. We can do what's called point cloud registration, iterative point cloud registration to collapse these models and construct visuals of these objects. Now, this was low res. We now have nicer sensors. And based on the examples that humans give the robot now collects and records a bunch of places where it should put the gripper in order to grab the object. Now, this data is really noisy because it's very easy, for example, to bump the object and then pick it up, but it corrupts the data in this database. And so what happens to the robot is that it collects a large database. Some of it is not very good. And so to deal with this, we have an automated system where the robot practices or ranks these graphs, it explores these graphs and ranks them. And when it's done learning, so there in the first set of videos, it was roughly, I don't remember, it was like 50% accurate in terms of successful grasping. Here in this second stage of these videos, I'm going to restart them. It misses one of the items once. I don't know why that's not playing. It misses this object once, and these two it's at 100% success. And we have some numerical results for these objects. But my favorite part about the studies, it's really like the only study that we've run where non-roboticists are performing as well as robotics graduate students at training a robot to, in this case, something simple, recognizing and picking up objects, but the performance is very, very similar. Yeah?
How do you judge the pressure with which the robot should?
So this particular robot does have tactile sensors on the gripper. It's still a power grasp, so it's all it is a claw. You can adjust the strength of the gripper like this, right? Using the tactile sensors. Most of the time it's not done, and most of the time it just squeezes roughly as hard as it can. And in hardware though, it is safe. I've stuck my hand in it while it's doing it. It doesn't injure you, but if you have a very fragile object, you'd have to start paying attention to the tactile sensors. Now those tactile sensors are not good enough to detect shear forces, which is slipping, right? There are sensors like that. They're less robust and more expensive, so they'll break a lot faster. So touch sensors are something that robotics just doesn't really have yet because we don't have anything robust and cheap. So it's very rare to have good tactile sensors for majority of robots at this point. It's going to get there, but it's not there yet. Okay, so I want to show you, this is going to, by the way, the next part, I'll show you one last part. You can't participate in any of our users in the next month of user studies now, okay?
So if you want to, then go out.
If you want your $10, you can come and do another study, user study later, but don't do a user study from my lab in the next month, because we're not done with this. But I wanted to show you, so that was old work. I want to show you what we're working on now. we've kept up a lot with this remote interaction, and it seems like it would be a solved problem, but yeah, this is 6 to 7 degrees of freedom in the arm, right? And 6 degrees of freedom in the orientation of the gripper. It's not that easy to specify. And what the field standard has been is this ring and marker model that you saw in the earlier video. If I go back to it, I'll make it play. So it's this ring and marker model where you're manually controlling every degree of freedom, right? You can rotate and translate all 3 degrees of freedom. So you end up with 6. And that's been like the field standard for a long time. And what that incorporates is no scene information. You actually leave all the mental work to the human. And then what we're exploring right now is what if we reduce the amount of control a human sort of has by incorporating more information about the scene. And now I feel like explaining it, it seems obvious what the answer will be, but there's a lot of reasons why we weren't sure where on the spectrum the best, this is a hypothesis, but that user effort will decrease and that it'll work better. But there's a lot of really interesting complications why that might not be the case. What we actually expected was something in the middle would work. I know I'm not making sense right now. I guess you need a little bit more info, but I'll show you on top of this video. So we came up with 3 interfaces to test. So I wish this screen was bigger, but this is a web interface. I think I can zoom in, can I? Did that work?
No.
Is that still play? I can zoom, but then I'm not playing it. That's sad. Alright, so you can always see the videos later if you want. We have 3 interfaces, so here everything looks the same. We recruited people to come and, again, work with different objects, but now the tasks are a lot more complicated than just picking something up. We're having them open drawers, unscrew bottle caps, pour things, and so on. So we're looking at more complex manipulation. And the first condition is the same ring and marker model that we saw before. In order to make it work, you really need 2 screens. One to show you what the camera feed, and one to show you this 3D rendering of the scene. And I'll show you a more high-res video of that in a little bit. And then let's see if I can fast forward here. No. So I'll just talk over it. Well, the other interfaces we tested involve various constraints. So in this one, the robot knows the depth to the items it's manipulating. In the third one, it actually, I'll just skip to the third one, it's actually calculating grasps. So this is how the robot sees the world. It's this kind of pixelated 3D view, and it's completely difficult to see from the back of the room. But when the user clicks on a point in the world, we can analyze the surface geometry around that point, calculate the normals, and figure out something called an antipodal grasp. Where can you stick the gripper in order to have the thing you're trying to grasp be stuck between the fingers, right? Roughly what humans do in a split second. This is something robots are just starting to do, or have been doing, but not well. And what we've done is create an interface based on that. Anyway, long story short, we're still designing this or finishing more analysis. But it's interesting that the old model that people have always used lets you do a lot less, right? It actually leaves you open for errors. So people take longer to complete a task, and they're able to complete fewer tasks in a given amount of time because they have to work do so much. So this is kind of an area we're still looking at with the goal. The reason we started working on this project is because we want to have people train more complex tasks over the web, and so we're looking at more complex interaction. We have other work on that I don't have time to talk about, more about trajectory learning from demonstration, so how to users physically move the arm and train trajectories and how do you represent trajectories that can be learned from human interaction. But I'm not going to jump into that right now, but this is more of a continuous path tech learning from. I'll just show you this part. If you teach the robot this way by physically moving it. But I'm going to skip that part. I'll just talk about my last slide. Just kind of the takeaway. Robotics is a really hot field right now, right? Robots are really starting to enter the lives of everyday people in education, in entertainment, and in at work and at home. And to me, adaptation and usability are really key factors, especially when taken together. Unfortunately, adaptation does not equal usability. And in fact, they're kind of opposite forces, right? It turns out because when a robot learns, it suddenly becomes unpredictable, right? Because it might try out new things, it might explore. It might not behave this second the way it behaved, 2 days ago. And so that doesn't usually add up to usability because people think of robots as machines that don't change. And so this is something that our field is currently struggling is how do you make systems that learn that are still, that we can trust, right? That are bounded, that are somehow limited in what they can do so that people don't lose their trust in them, they're not scared of them, and that robots don't break our world and break our stuff because then nobody wants to use them. So this is kind of, it's a chicken and egg problem. We want this, but we don't know how to yet make it happen. Anyway, thanks so much for your attention. Those are some of the students from Georgia Tech whose work I talked about. And I think I have like 30 seconds for questions, or I can stick around as well.
So I don't know if you have much time for questions, but one thing I would say is you talk about perception, and you said computer vision is a whole field. Perception is also listening, and you have a room here